Hi there. Welcome to class. This is Mrs. Brunk. And today we're going to be talking about solving absolute value equations. And I'm just going to warn you, my cute little pug Harlow is laying next to me and she's doing all kinds of chewing and lots of loud noises. And she probably is going to be snoring here in a minute. So I just wanted to let you know ahead of time if you hear any weird noises in the back. That's just my dog. So like I said, we're going to be studying about solving absolute value equations. And our essential question is this: how can you solve an absolute value equation? So that seems to make sense since that's what the lesson is about. And we're going to be taking a look at a couple different ways to solve. First being solving by a graphic method. So an absolute value equation differs from a linear equation in that they have two solutions. That's the key you want to think about is, I guess I'd say almost all absolute value equations have two solutions. This is indicated with what's called a disjunction. And a mathematical statement is a disjunction if it's connecting two other statements with the word or. To see why there can be two solutions, you can solve an absolute value equation using graphing. So we just got done talking about how to graph an absolute value function. And so if we wanted to solve this equation, 2 times the absolute value of x minus 5 minus 4 equals 2, graphically, what we could do is we could take a look at each side of the equation separately, graph it, and see where they cross. And graphically, that solution would be the shared points on those two graphs. So essentially what we're going to do is we're going to graph this as one function and this as another function. Maybe we'll call this one g of x. So we're going to graph both of these on the same coordinate plane and see where, in fact, if anywhere, they cross, what point they share in common. So taking a look at the absolute value side, we can see that the vertex is at 5, negative 4. And there's this slant or steepness of the branches of 2. So I could plot that vertex at 5, negative 2. Sorry, 5, negative 4, which would be right there. And then we could use that slope of 2 to rise 2. So I could rise up 2 and run 1. And then rise up 2 and run 1 to the left, which would put a point right there. I could connect them with straight lines to make the absolute value graph. And that would be the graph of the left-hand side. Now I'm going to go ahead and I'm going to graph the other side. And when looking at that other equation, g of x is equal to 2, that's like saying y equals 2. And hopefully you remember that any time you just have a y in your equation and not an x as well, it really just means that it's only going to cross the y-axis, and the only kind of line that does that is a horizontal line. So this is actually going to be a horizontal line at y equals 2, which would be right here. And when I draw it, I can already see why there's going to be two solutions. I can see that these two graphs cross at this spot right here and that spot right here. And since when I'm solving, I'm actually looking for the values of x, I'm really just looking for the x coordinate of those points where they cross, and I can clearly see that one of them is at 2, and the other one is down here at 8. Now you can check both of those solutions by plugging them back in to the original equation, and you'd see that in both cases, when I substitute back in the absolute value side, they are equal to 2. So 2 times the absolute value of 2 minus 5 minus 4 would be the 2 minus 5 is negative 3. Absolute value of negative 3 is 3. 3 times 2 is 6, and 6 minus 4 is 2, so that checks. And then as well as when we put 8 in. 8 minus 5 would be 3. Absolute value of 3 is 3, times 2 is 6, 6 minus 4 is 2, and so we can clearly see that those are the coordinates of the solution, and they are the two values that when I substitute back in, make that equation true. So that's really how to solve an absolute value equation graphically, is to try to just take the one side and graph it, which is going to be the absolute value v, and the other side, which will be a constant function, a horizontal line, and just simply see where the two graphs cross, and read from the graph the x value, which would be the solution. So I'd like you to go ahead and pause the video and take a few moments to reflect on the following questions. Number 1, why might you expect most absolute value equations to have two solutions? Why not 3 or 4? Number 2, is it possible for an absolute value equation to have no solutions? One solution? If so, what would each look like graphically? So if you kind of think about what we just did with the graph, I mean, you might think graphically, if it didn't have any solutions, it might be where, say, this horizontal line was, instead of actually hitting the absolute value graph, say it was down here, like that. And you'd see it would never cross that, and there'd be no solutions. Or what about if instead the line went through and hit just there on the vertex? Then that might cause the equation to have just one solution. So you can see where there would be no solutions, where there'd be that one solution, and then clearly you can see why there would be a possibility of two solutions. So take a moment, pause the video, and respond to these two reflection questions. Now we're going to take a look at solving absolute value equations algebraically. So to solve absolute value equations algebraically, the first thing we're going to do is isolate the absolute value expression on one side of the equation, the same way that you would isolate a variable in, say, a linear equation. Then we're going to use this rule. If the absolute value of x equals a, where a is positive, then x equals a, or x equals negative a. So we're basically going to write two equations that considers the two possibilities, that the value inside the absolute value is a positive number, and of course when we take the absolute value of a positive number we get positive, or maybe the value of that absolute value quantity is negative, and when I take the absolute value of it I also get a positive. So we're just going to consider those two possibilities, and notice the use of a disjunction here in the rule for the values of x. You cannot know from the original equation whether the expression inside the absolute value bars is positive or negative, and so since we can't tell it's positive or negative, we must work through both possibilities and consider the two different directions we could be going. So let's take a look at this equation. Absolute value of 3x plus 2 equals 8. And so that first step, which is isolating the absolute value quantity, which means I want to get this all by itself, and in order to do that I would have to then get rid of the 2, so I would subtract 2, making this be the absolute value of 3x on this side and 6 on the other. And once you've got the absolute value isolated, you're going to write the two possibilities, and that first one will be that 3x could equal 6, as it appears here without the absolute value brackets, but because we know that absolute value brackets could take something negative and make it positive as well, then 3x could also equal negative 6. And solving those by just dividing by 3, solve them both the same way, but the outcomes are going to be different because 6 divided by 3 is 2, and 6 divided by negative 3 is negative 2. And so there are the two solutions that you see graphed here, one at negative 2 and one at positive 2 are my two solutions. Let's take a look at another example of solving algebraically. So of course we want to isolate the absolute value first, and we have to follow these reverse order of operations as we're doing so. And so the first thing we would want to do is we want to undo any adding or subtracting. And so by adding 2 to both sides, on the left-hand side we'd be left with 3 times the absolute value of 4x minus 5. And on the right-hand side, 19 plus 2 is 21. So the next step would be to go ahead and divide that 3 off so we can get the absolute value alone. And that leaves us with absolute value of 4x minus 5 equals 7. But what that tells us really is, because I'm taking the absolute value of something and I get 7, that quantity, this quantity right here, could equal 7, that 4x minus 5 could equal 7. But on the other hand, 4x minus 5, minus 5 could also be equivalent to negative 5. And solving those, they have the same steps, but they come out with a different result. So if I were to add 5 to both sides to get 4x equals 12 and divide by 2, I can see that x must be 3. And then on this one, adding 5 to both sides is going to leave me with 4x equals negative 2, and dividing that both sides by 4 there, it's going to give me that x is equal to negative 2/4 or negative 1/2. So to kind of relate that back to that first method we learned, which was the graphing way, if I had graphed this left-hand side over here, and then at the same time I graphed this horizontal line at 19, we would see that they would cross 2 places, one when x was 3 and one when x was negative 1/2. And of course we could plot these values on the number line to represent our solutions. So the next 2 problems are your opportunity to give this a try independently. So I want you to solve each absolute value equation algebraically, graph the solution on a number line. So go ahead and pause the video, try questions number 3 and 4, keeping in mind all the things we just talked about, and then tune back in to check your work. Pause the video now. Alright, so thanks for giving those 2 problems a try, and hopefully you experienced some success. And you found that the solutions to number 3 were 18 and negative 22, and the solutions to number 4 were 8/3 and 4/3, and so to graph 8/3, which is approximately, well, it's actually 2 and 2/3, which would be right about here. See, these are scaled by 2/3, so 2/3, since this is scaled by 2/3, if I had 2/3 and 2/3, that would be 4/3, so that's 2 tick marks here over to the right to represent the 4/3, and the 8/3 would be right over here. Right there, 8/3. So the final thing we're going to look at today is we're going to explore absolute value equations with fewer than 2 solutions. Now we actually found, we already had one where there was just one solution, and that was that one that graphically means that that line crosses right through the vertex. But now we're going to take a look at, what about if there are no solutions, and what would that look like? So let's go ahead and look at the next page and some examples of that type of equation. Okay, so you have seen that absolute value equations can have 2 solutions when the isolated absolute value expression is equal to a positive number. When the absolute value is equal to 0, then there is just a single solution because 0 is its own opposite. But when the absolute value expression is equal to a negative number, there is no solution because absolute value is never negative. So it would just be a contradiction to say that the absolute value of something was equal to a negative number. So what we're going to do is go ahead and take a look at example 2, which asks us to isolate the absolute value expression in each equation to determine if the equation can be solved. If so, finish the solution. And if not, then instead write no solutions. So taking a look at this equation, the very first step to isolating the absolute value is to undo any adding or subtracting. So using that SAD map, reverse order of operations, I'm going to undo any adding or subtracting first. And that's going to leave me with negative 5 times the absolute value of x plus 1 is equal to 10. So now I'm going to go ahead and divide both sides by negative 5. And again, our goal is to try to get the absolute value isolated. And so when I do that, the left-hand side is now just the absolute value of x plus 1, whereas the right side is 10 divided by negative 5, which is negative 2. And so now when I consider that statement, something about it just doesn't jive, because it's saying I am taking the absolute value of something and I'm getting a negative number. And we just know that simply cannot happen, that the smallest possible value you could get when taking an absolute value is to get 0 or anything positive. So that's an indication that there is no solutions to that. Now we could actually write no solutions. I've also seen it notated like this, which just means null set or no values in the set. Let's go ahead and try one more example. So this time the equation looks much more complicated, but we can essentially use the same steps, and that's step number 1, isolate the absolute value quantity. But that's going to involve undoing a lot more operations, the first of which is undoing the subtracting of 3 here off the end. So I'm going to undo that by adding 3. And that's going to leave me with 3/5 times the absolute value of 2x minus 4 equals, well, when I add 3 to both sides, it actually cancels out the negative 3 on the other side, giving me absolute value of 0. So then the final thing I have to do to isolate the absolute value is to multiply both sides by the reciprocal of 3/5, which is 5/3. And 5/3 times 0 is 0, so that just leaves the right-hand side as 0 and leaves the absolute value of 2x minus 4 on the left-hand side and 0 on the right. Now this is where I would normally write those two special cases, but in this case, because it says the absolute value of 2x minus 4 is equal to 0, there is not a separate possibilities. We can't say it equals 0 or negative 0, it just equals 0. And so we're simply going to solve one case. 2x minus 4 is equal to 0. It's kind of like graphically when we saw the scenario where we could get one solution with the line just crossing through the vertex. So that's what's obviously happening here. So we're going to go ahead and add 4 to both sides, leaving with 2x equals 4. Divide by 2, and I get x equals 2. And I can go ahead and check it by substituting it back in up in the equation. And I'm just going to real quick talk you through that check. So first, when I would plug it in, I'd have to do the absolute value part right here. So that would be 2 times 2, which is 4, minus 4, which is 0. The absolute value of 0 is 0, multiplied by 3/5 is 0. And then minus 3 would equal negative 3. So it checks up in the original, and we know that means that's our solution then. And just 1 this time, just x equals 2. So this time if we were to do a graph of the solution on a number line, instead of there being 2 points as there was in the prior example here, there's just going to simply be 1 point, and it will be at x equals 2.